All right. Good evening, everyone, and welcome to the show. My name is Anant. I'm a professor of economics at UW-Madison, and I run a center called CROWE, the Center for Research in the Wisconsin Economy. We usually write about nerdy stuff like the impact of tax reform. We wrote on the impact of tariffs in the state of Wisconsin. I doubt anybody actually read those white papers, but a couple of weeks ago, we put something out titled The Economic Implications of Badger Football's Underperformance. And gosh, I mean, it had more hits and it had more media mentions than all the other papers I've ever written combined. So kind of moving from there, what is CROWE doing hosting speakers with the objective of effectively promoting viewpoint diversity, and why? So about a couple of years ago, I began this initiative, for lack of a better word, I kind of called it a sifting and winnowing series, where we basically are we charge myself with the objective of promoting viewpoint diversity. Why? Public support for UW's system is at an all-time low, with Marquette polls indicating that other state priorities have surpassed interest for UW over the past few decades. So in the Marquette polls, we kind of rank, when you ask Wisconsinites, how much do you care about UW's system? We kind of rank between I don't know and I don't care. It's not very different nationally. When you look at Gallup polls, it shows that only about 36% of Americans have a great deal or quite a lot of confidence. When asked why, the answer is faculty have political agendas. So is there any truth to that? I'm going to pick on Scientific American for good reason. Scientific American, which has been in continuous publication since 1845, featured great minds such as Einstein and Oppenheimer. Some articles in the magazine have denounced the clearly beneficial public health goals, such as reducing America's sky-high obesity rates, as racist. It criticized President Trump's support for a work requirement as a condition for Medicaid eligibility. And by contrast, the editorial says that Ms. Harris's support supports science and would improve health by expanding Medicaid coverage. Apparently, whether the welfare state increases health or not is not up for debate. As Vanderbilt University Chancellor Diermeier warns, we have to be extremely worried that standards of scholarly excellence are being undermined by political position taking. Your favorite CNN's Fareed Zakaria echoes this. America's top universities should abandon their long misadventure into politics, retrain their gaze on their core strengths, and rebuild reputations as centers of research and learning. To do what we can to promote intellectual diversity, CROWE has invited Speaker Voss to talk about the University of Wisconsin system funding, Heather McDonald and DEI initiatives. We recently organized a panel on NIH funding cuts. We even had a speaker talk about the debanking of America. In 2021, Steve Koonin published Unsettled. The book drew sharp ad hominem attacks rather than substantive rebuttals. For instance, an opinion in Scientific American, signed by 12 academics, branded him as a crank who's only taken seriously by far-right disinformation peddlers hungry for anything they can use to score political points. This exemplifies polarized academic discourse where nuance is dismissed as stifle debate. And instantly I knew I had to have Steve over to give a talk. It is now my great pleasure to introduce our speaker. So ground rules, I think Stephen's going to talk for about 45 minutes. There will be time for an open Q&A. The microphone is up there, so if you want to ask a question, please head over there and engage. A renowned theoretical physicist and a leading voice in the intersection of science, energy, and policy, Dr. Koonin brings a wealth of expertise and a commitment to rigorous, evidence-based discourse on some of the most pressing issues of our time. Born in Brooklyn, New York, Dr. Koonin earned his Bachelor of Science in Physics from Caltech in 1972 and his PhD in Theoretical Physics from MIT in 1975. His illustrious academic career includes over 3 decades as a professor at Caltech, where he served as provost, shaping the institution's research and educational landscape. He is the author of the seminal 1985 textbook, Computational Physics, which remains a cornerstone in his field. Dr. Koonin's contributions extend far beyond academia. He served as chief scientist at BP from 2004 to 2009, and as undersecretary for science at the US Department of Energy from 2009 to 2011 under President Obama. In these roles, he oversaw critical research in climate, energy, and national security. More recently, he has been a university professor at NYU with appointments at Stern and the Tandon School of Engineering. In 2024, he joined Stanford's Hoover Institution as the Edward Teller Fellow, continuing his work on urban science, climate, and energy policy. Dr. Koonin is perhaps best known to the public as the author of Unsettled. His recent involvement in a DOE climate working group report further underscores his focus in clarifying uncertainties in climate science for informed policy making. Despite some unfair and often politically charged critiques from outlets like Scientific American, Dr. Koonin remains a steadfast advocate for transparency and scientific integrity. After all, true progress comes from questioning assumptions, prioritizing facts, and sifting and winnowing. We're very fortunate to have Dr. Koonin here at UW-Madison to share his perspective on climate and energy. Please join me in welcoming Dr. Koonin to the stage.
Thank you. As a coda to the Scientific American story that Ananth just mentioned, I had the opportunity to debate one of the dozen or so authors of that piece about 3 years ago. And toward the end of the debate, I put the article up. Andy Dessler was the guy who's a professor at Texas A&M. And I said, Andy, do you really think I'm a crank and a shill? And he immediately denied having authored the article at all. Such is the state of the public debate on these matters. So I've been trying to elevate things a little bit by bringing a set of facts to the table, trying to educate people about both climate and energy, which are both complicated and nuanced subjects. So I hope you'll bear with me for the next 40 or 45 minutes. Everything I will tell you comes either from the primary data, the research literature, or the official UN and US government reports. So let's start off with the notion that the climate is changing. I show you here a graph of the average surface temperature of the planet from 1850. Let's see, is this going to work? How do I move the pointer? That's a good question. If I point it at the screen, does it move? All right, anyway, all right, there we go. This is the average surface temperature of the Earth as measured or inferred from 1850 until last month, I guess. And what you see is that it's risen by about 1.5 degrees, although it is not a smooth rise. It was pretty constant, allegedly, in the late 19th century, rose pretty rapidly from 1910 to 1940, actually went down a bit from 1940 to 1970, and then up again pretty sharply from about 1980 to the present. At the same time, human influences on the planet have been growing. This shows the carbon dioxide concentration in the atmosphere, and it has gone from about 280 parts per million before the Industrial Revolution started up to just about 420 or 425 today. This carbon dioxide exerts a warming influence on the planet, but you can see things are not so simple because the carbon dioxide has gone up monotonically while the temperature has got ups and downs. And untangling the causal relationship between these two graphs is one of the great challenges in front of us. So what do we do about this situation? Through policy, through technology development? The answer is we've got to strike a balance. On one side, we've got the certainties and uncertainties in our understanding of how the system responds to human influences and the hazards, risks, and benefits to society and ecosystems that understanding poses. On the other side, as I'll describe, we've got the world's growing demand for affordable, reliable, and clean energy. And these are often in tension, and in resolving that tension, we've got to do a set of policies that embody the values and priorities that we have, our tolerance for risk, equity between generations, and the efficacies and costs of various responses. As you'll see, you can do some things that you think might be doing some good in a situation that are very costly and in fact have very little effect on the outcome. So I'm going to try to frame my discussion in terms of three high-level statements. The first is that the notion of a climate crisis has scant scientific support. Today's climate is not broken, despite what you may read in most of the media or from many of the politicians, and the fears of future catastrophic changes depend upon extreme scenarios that are fed into models that are entirely unsuited to the task. The second is that advocacy for overly rapid global decarbonization is immoral. And the third is that overly rapid national decarbonization is disruptive, expensive, and will degrade national security. And I'm going to try to support each of these statements with facts, not feelings. All right, well, let's start off just by remembering exactly what climate is. The weather changes from day to day, or perhaps season to season. That's not the climate. Climate is the long-term statistical properties of weather, typically over several decades, conventionally 30 years, 3 decades. That's well illustrated by this chart, which is the height of the Nile River at its minimum every year, as measured at an island in Cairo, Rhode Island, starting from about 1640 or so up until 1450, so 800 and some odd years. The blue lines are the year-to-year averages, and the red line is the 30-year running average. And you can see from the blue lines that there's a lot of natural variability up and down from year to year. Some years it's as high as 6 meters, and in a few years before that it was down to 1 meter. Right? That's weather. The 30-year average is the climate, or at least this aspect of the climate system. And you can see that it still changes all on its own. Needless to say, human influences were entirely negligible during this time, at least in terms of greenhouse gases. And nevertheless, you see from, let's say, the beginning of the chart up until the latter part of the 8th century, that the minimum declined. And you can just imagine some medieval Egyptian climate panel screaming, "New normal, and we've got to do more prayers and sacrifices." And if you just waited 100 years or so, things would have come back up again. So natural variability in the climate, not the weather, the climate, is something that one has to contend with and understand before you can point at something and say, aha, that's CO2. It's kind of humbling, actually. There's new normal in Arabic. Okay, so let's look at what the UN Climate Panel had to say in its most recent report, which came out 2 or 3 years ago. Here's a table from the report that lists about 30 different extreme weather kinds of events, starting with heat waves, cold waves, and hot and dry, floods, droughts, storms, etc. And what is shown is whether a climate trend has been detected in each of these events. And what is surprising, we'll talk about some of them in detail in a moment, but what's surprising is most of these entries are blank. Namely, in most types of extreme weather events, we have not detected a statistically significant trend. Now, some of the critics of what I've been saying and many other people have been saying are that, well, we haven't looked, or the record is not long enough. Well, you can be sure if there was a significant trend, somebody would have studied it already. And even if there isn't a trend, the fact that the media report that the climate is broken is a severe misdirection of non-experts. So let's have a look at some of these. This is data on hurricanes. In the upper panel, it shows the number of hurricanes from about 1981 up until the present. The lower trace is the number of major hurricanes on the top, and then all hurricanes on the upper trace in the upper panel. And you can see there is no long-term trend. if you try to fit a line to it, there's no significant slope. The bottom panel is a different measure of hurricane intensity, which weights each hurricane by how big it is. And again, there are ups and downs, but no long-term trends. And if you look at the official reports, they say there are no long-term trends in the intensity or frequency metrics. This is surprising because if you watch the network news or read some of the newspapers, every hurricane is a symptom of climate change and the disastrous impacts of human influences. Not true. We have in the US a wonderful record of weather at stations around the continent. Some of them extend back to 1871. And they've been assembled into what's called the US Historical Climate Network. There are about 1,200 stations, records about 150 years for some of them. That's where they are. And one of my colleagues, John Christie, who is at the University of Alabama in Huntsville, is the world's expert at digging into these old records and extracting information about the climate. So here's something interesting he found. You will recall that around July 4th of this past summer, we had some awful, awful floods in Kerrville, Texas. The Guadalupe River rose up suddenly and wiped out some terrible number of people and camps that were there. This is the Weather Observer's record from July of 1900 at Kerrville, Texas. Right? So 120 some odd years ago. And you can see day by day, going down the left hand, the observer dutifully recorded the maximum and minimum temperature, and then in the fourth or fifth column over the amount of precipitation. And you can see it's pretty dry, but if you get to the 14th and 15th, you can see that there are 12 inches of rain dumped in that 1.5 day period. And it's amusing to read the observer's notes, which are in script there on the right. I'll read it for you if you can't see it. Severe rainstorm on the 15th, causing 33-foot rise in the river at this station, the highest the river has been since 1866. Okay, so this happened 120 years ago, almost the identical event to what we saw this summer. And of course, human influences were essentially negligible then. In fact, if you look at the record of heaviest rainfalls at that station in Kerrville, Texas, you can see that the 2025 event wasn't much at all. Most of the rainfall happened somewhat upstream. But nevertheless, the point is that this is called Flash Flood Alley for a reason. This neglect of the historical record is endemic in the official reports. In September, the National Academies of Science put out a report somewhat in rebuttal to the DOE report that Ananth mentioned. I'll tell you about that report in a minute. But the opening sentence of that report links the Kerrville flood of this year with climate change. Nonsense. That's why I get so mad when the science is misrepresented. Here's another one. This is an official graph from the US EPA. This is under the Biden EPA, not the present one. They haven't changed it. It's the same there. It shows the incidence of heat waves across the US. We can go into the definition, but it's a consistent metric across 130 years. And again, what's surprising is that the heat waves today, in the last few years, are no more common than they were around 1900. And that the greatest incidence of heat waves was during the 1930s. Again, human influence is rising monotonically during this time, kind of calls into question whether humans are having any influence on this or not. This is a regional variation of heat waves. It's, again, kind of interesting. If you divide the country into the West, the East Central, and the country as a whole, what you see is that the 1930s heat waves were mostly there in the central and east part of the country, and that in the later decades, the heat waves have been growing in the West. All right. There are fundamental things we still don't understand about the climate system. This shows the global temperature since about 1980 as measured by satellites. And what you see, it's going up. And the last couple of decades have been particularly warm. The conventional story is that it's the growing amount of carbon dioxide in the atmosphere that's preventing the heat from being released. And so the planet's getting warmer by increasing the infrared opacity of the atmosphere. But there are folks who measure how much sunlight the planet absorbs, as shown in this graph. And what one finds for the last 20 years or so is that the planet has been absorbing more sunlight. Clouds are getting a little bit less. That's completely contrary to the conventional story that we warm because of the retention of heat, not because of the absorption of more sunlight. So this is still an ongoing discussion in the climate science community. It just shows that there are fundamental things we don't understand. Why is it that we can't understand this? The answer is that the human influences are about a 1% effect on the Earth system, and understanding a complicated, chaotic system for which we have poor observations at the 1% level is a real challenge. Let me show you what we do to try to understand what's going on with the climate. As I mentioned, human influences are about a 1% effect. The way in which we try to understand how the system responds to that 1% perturbation is by cutting the globe into squares, about 100 kilometers on a side currently, building voxels, boxes, maybe 20 layers up into the atmosphere, and then another 6 to 10 layers down into the ocean. We build a grid that covers the atmosphere and the ocean. It winds up that we've got about 10 to the 8th voxels. And then we use the basic laws of physics, conservation of energy, momentum, mass, and to follow the matter and radiation through those voxels time step by time step. You wind up using about 100 million voxels, taking about 100 million time steps, 10 minutes at a time over centuries, and you need to do this with 10 to the minus 3 precision to understand the response. The world has a multitude of models, about 50 of them, formed by different groups around the world. There's the Canadian model, and the US, of course, has several models. The Russian model, which turns out in many respects to be the most accurate. And they disagree with one another, and they disagree with the data on average. Why? Well, one of the main reasons is that when we cut the globe into these boxes, there are still many phenomena in the climate system that happen on a smaller scale. If the box is 100 kilometers on a side, think about the thunderheads that might be happening within that box, particularly in the tropics. Those are a couple kilometers wide. You cannot describe them in detail because you're only trying to describe the whole box. And so you have to make what are called subgrid assumptions about how many clouds are there, where are the clouds, what's the variation of humidity or temperature through the box, and so on. Different people make different assumptions, and so you get different models. There are also feedbacks that are difficult. When the globe gets warmer, some of the ice disappears, and that increases the absorption of sunlight, for example. Or as the globe gets warmer, it holds a little more moisture in the atmosphere, more clouds, where are the clouds, et cetera, how do they affect the heat and light flow. So those feedbacks are also difficult. There are long-term variations, and what's disappointing is that if you look over the last several generations of models, they have not really converged. They haven't gotten any better in describing the data or in agreeing among themselves. Let me show you some of that. This shows about 40 models, and what's plotted for each of the models is what's called the climate sensitivity. Namely, if you doubled carbon dioxide and let the model come to equilibrium by how much would the temperature go up at the surface on average. And you can see that it ranges about a factor of 3 from 1.8 to 5.6. Right? Needless to say, this number is very important because if the globe only went up by a temperature 1.5, 1.89, it wouldn't be much of a big deal, whereas it went up by a factor of 5.6, it would be serious. And in fact, the IPCC, the UN panel, throws out those models in yellow. It just says they're too sensitive. That's pretty disappointing when the world's best modelers try as hard as they can and still can't agree with one another to within a factor of 3. How do they agree with the data? Well, there are lots of graphs here. This shows the history of the global temperature over the last 120 years. The black lines in each of the graphs are the observed temperature. They're the same in each of the graphs. But the yellow lines are the band of the different models. And the models have been segregated into low sensitivity models in the left-hand column, to medium sensitivity and high sensitivity models on the right. And you can see it is the low sensitivity models that do the best job of agreeing with the data. Well, what about, that was a global measure. What about other measures? Let me not do that one. Let me talk about this one, perhaps of interest here. You can take the 10 states in the middle of the country and ask how much have they warmed over the last couple of decades. And that amount of warming, or the trend actually in degrees per decade, is the blue bar at the far right of that right-hand graph. The different models are the red bars, and you can see that none of the models reproduce the trend. All of them are much too sensitive. Now, you can say, well, you just picked one region out of the country. You should look at the whole globe. I showed you some results for the whole globe. And for the US economy, needless to say, the Corn Belt is particularly important. And so the models get it wrong. They're too sensitive on average. In order to project what's going on in the future, we have to make some assumption about human emissions over the, let's say, the next century. And what this graph shows is that we have consistently overestimated what the emissions will be. If you start from the models in the 1970s, you can generally see that they overestimate what's actually happened up until today, which is the black line. Let me not go through that one. Still, there are really interesting predictions of effects. This is a prediction about sea level rise, and I will focus in on one region which is particularly dear to me since I live part of the time in New York. At the southern tip of Manhattan, which is called the Battery, there is a tide gauge, and it's been there since the middle of the 1850s. And this shows the monthly height of the sea level for every month since the middle of the 1850s, except for that gap in the data in the 1880s. And what you see if you try to fit a straight line to it is a pretty steady rise at just about 3 millimeters a year. What's 3 millimeters a year? Well, that's a foot a century. Okay? And it's something that New York City has been pretty good at adapting to over the last 150 years. One of the things that's of interest is the rate of rise. And you can do a simple fit 30-year trailing slope for each of the points in that graph from about 1920 going forward. And you can see that the average rate of rise in millimeters a year averages about 3 millimeters a year, as I told you. But it shows some big ups and downs, as low as 2 millimeters a year or as high as 5 millimeters a year. Exactly what the cause of that is, nobody knows. Maybe long-term oscillations in the North Atlantic, because other tide gauges on the US East Coast show a similar oscillation. And what's interesting is that NOAA, in 2022, put out a report saying that by 2050, sea level would rise by a foot. Okay? And you can see that that's about 3 times the average rate. Well, we'll know pretty soon whether that prediction is correct or not, as shown by the red star over there, because it's got to start rising pretty soon if that's the case. And as I like to say, who am I to dispute Noah? Okay. And, you know, the research literature says don't trust any of this. Here's a paper by Nissan in 2019. The use of climate models to guide local practical adaptation actions is unwarranted. Climate models are unable to represent future conditions very well, and they give a false impression of confidence to users. Right? So do not trust the models. Okay, well, what effects might we expect from warming? We can say something about that as well. Here's that same temperature record that I showed you before. And what you can see is that the globe has warmed about 1.3 degrees since 1920 or so, the last 100 years. And while we can't really predict what's going to happen in the next 100 years as the globe presumably continues to warm, we can look to the past for some guide. And comparable warming of about 1.3 degrees is projected to the end of the century. So what will the impacts be? Well, somewhat surprisingly, the globe has prospered since 1900 like never before, even though, or perhaps because, the globe has warmed 1.3 degrees. Here are some metrics of human well-being. The population is 5 times larger now than it was at the beginning of the 20th century, with about 8-point-something billion. Life expectancy went from 32 years in 1900 to 73 years. The literacy fraction is 4 times larger now. 86% of the globe knows how to read at this point. The GDP per capita went up by a factor of 7 when you adjust for inflation. Food production is up by a third. We can feed the whole planet now. Extreme poverty has gone down spectacularly, and even more spectacularly, the death rate from extreme weather has gone down by a factor of 50 due to more resilient infrastructure and better ability to predict storms and floods. Okay? It's hard to say that this warming of 1.3 degrees has harmed the globe very much, and it beggars belief, at least my belief, that another 1.3 degrees is going to significantly derail this progress. We are wonderfully adaptive as a species. You often hear that people are dying from more heat waves. Well, that's true, but a lot more people are not dying because of fewer cold waves. And in fact, the net of deaths from extreme temperatures is a decrease in deaths by a significant amount. This shows it from some paper in The Lancet, country by country. What about agriculture? Have we seen food yields crash? No, not at all. This is yield, land use, and population for the globe over the last 60 some odd years. And you can see, we keep producing more and more food, whatever detrimental impacts the warming has had on agriculture. Monetary losses. If you scale the losses from extreme weather by the GDP, as we get richer, there's more infrastructure that can be clobbered. They're actually going down slightly and are at the level of about 0.2%. So not very much. We are just getting more and more resilient. I like this graph, and I think this is the last one about impacts. This is a graph that appeared in a White House report by the Biden administration. It was in 2023. And it shows the projected decline in the US GDP in percent, not the decline in rate, but the decline in the GDP itself, as a function of the global warming relative to today. And what you can see is that I'm sorry, not relative to today, but global warming relative to pre-industrial. We're at the vertical line right now, and okay, maybe 4 or 5 degrees, perhaps, in extreme cases, you might see at the end of the century. And what's shown is a dozen different models. And the black line is the average of these models. And what is remarkable is that the vertical scale is measured in a couple of percent. In other words, if the globe warmed by 4.5 degrees Fahrenheit at the end of the century, let's say, the GDP would be smaller by 1 or 2% than it would have been otherwise. Never mind that at 2% a year expected growth, the GDP would be 4 times larger at the end of the century. All right? So instead of 400%, it would have been 380-something%. You cannot project with this accuracy, but the point is it's small. Nevertheless, you had President Biden talking about existential climate threats at the same time as the CEA and OMB were putting out this graph. All right. Just a word about this report, which you can find on the web. Secretary of Energy Wright chartered a group of 5 of us, 4 scientists and an environmental economist, to put out a report about those aspects of climate science that were misrepresented in the popular dialogue and the media and the political discussions. And we did. You can find it on the web. As Anant said, it immediately generated great pushback from scientists, national academies, and so on. Most of the criticisms, as we've looked at it, were about nuance and detail. We will put out a revised version by the end of this month, we hope. But it just shows you that we were over the target, let's just say. We got a lot of people really upset. You know, there's this famous line from Einstein. When Einstein was doing his work in the 30s, it was criticized in Nazi Germany as Jewish science. And some large number of German scientists wrote criticisms of what Einstein was doing. And Einstein said, you know, if I were wrong, it would have taken only one scientist to refute me. So I sort of have that feeling now. Okay, we'll get it sorted out. Okay, second one. How are we doing on time? About another 5 minutes? Yeah, 10 minutes. All right. I want to just, advocacy for rapid global carbonization is immoral. You often hear that it's immoral not to reduce carbon emissions. Well, it's immoral not to provide energy to people who need it. This shows global emissions over the last 50 years going up. Most of it is CO2, and most of it is from the burning of fossil fuels. This shows what we would have to do by 2050, allegedly, in order to stabilize the temperature at what some people think is a safe level. Population is going up. Global population is 8. It'll probably top out at about 10 by the end of the century. So that's one factor in growing energy demand. The other is development. This shows for various countries how much energy each person uses per year against the GDP per capita in constant dollars per year. And what you see is that for the developing world, which is down in the lower left, the poor parts of the globe, the energy use increases steadily and universally as countries develop. And there are many things to learn about this chart. I don't have the time to go into it. But what is sobering is that 50% of the world's population is down there. And if those folks are going to improve their standard of living, they're clearly going to need a lot more energy than is currently available to them. In fact, energy consumption is projected to go up by about 50% by mid-century. And most of that energy, if we continue on the current trajectory, is going to come from fossil fuels. Right? They are the most reliable and convenient way to get energy to the developing world. We have spent, I don't know how many trillions, multiple trillions of dollars trying to reduce the fraction of fossil fuels in the world's energy mix. And this shows that fraction. Today, more than 80% of the world's energy comes from fossil fuels, about the same number that was there in 1970. So it's really hard to reduce emissions and still provide the energy people need. Let's say a word about wind and solar generation. It is true that wind and solar are the cheapest ways of producing electricity, but they are not the cheapest ways of producing reliable electricity, and society needs reliable energy to function. This shows the graph of wind generation in the UK, 6 months straddling October to March of 20 to 21. And what you see is that the output day by day varies a lot, but there are long periods, as long as 11 days in the right-hand side, where the wind just doesn't blow at all. These are, and it turns out that often the sun does not shine at the same time. These are called Dunkelflaute in German, which means dark stillness. If you want your electricity to be reliable, you had better have some backup system that will fill in for the wind. Gas, for example, nuclear. And it turns out these can be quite long, and so the backup system has got to be pretty capable. That backup system winds up costing more than the wind and solar, and so you've effectively doubled or tripled the cost. And so wind and solar are not the cheapest way of producing a reliable electricity system. I'm not going to talk about that. Okay, last one, downsides of overly rapid national decarbonization. Energy touches everything, everywhere, all the time, and so there are lots of people who have a voice in what the energy system should look like. They evolve slowly, only over decades, because the facilities are expensive, they last a long time, they need to work with one another, and so you tinker with it at your peril, like trying to deploy too much wind and solar, or trying to deploy electric vehicles too rapidly. Attempts to accelerate an energy transition will be extraordinarily disruptive. We have seen that already in Germany, in the UK, and I can go into the details, and here in the US as well. You degrade the cost and reliability, and you change domestic employment, and you also change the way funds flow. For example, gasoline taxes are an important source of revenue. If you're going to run everything on electricity on the roads, you better find a way of making up the gasoline taxes, for example. Domestic manufacturing increases, costs increase. As you may know, both the UK and Germany have been deindustrializing rapidly. A major factor in that has been the cost of energy for them. So slowly. I think what we've seen, let me just, because we're running out of time, we have seen the relaxation of mandates. There's my phone. The relaxation of mandates, disappearing of subsidies, consumer pushback in France, Germany, UK, Netherlands. Here in the US as well, I think it's become a political factor. I saw the political advertisements for the New Jersey gubernatorial race in the last couple of weeks, because I lived part of the time in New York, and the cost of energy was a major factor in that political discussion. Okay. I like to use this cartoon for describing the energy transition today. We had great aspirations and went charging off, and suddenly realized that there were some fundamentals that we had forgotten about. Again, let me not go through this, but I can talk about them later on. But I would summarize it by saying that climate, as we think about energy, ain't nothing, but it certainly isn't everything. And affordability and reliability are more important than greenhouse gas emissions. I'm going to, because I'd like to get to questions, I'm going to stop at this point. But let me just say that the facts and the logic I presented to you, I think, are pretty unassailable. and they're starting to get through in the discussion. As you might have seen last week, Bill Gates did a U-turn in his thinking about these things, and I think articulated a position that's pretty close to what I and more than a few others have been saying for a decade or so. And slowly, the data on the climate and the technoeconomic realities will prevail, but hopefully we will not do too much damage before we come to our senses. All right, with that, maybe I'll take some questions.
I'd like to open it up to questions. Go ahead.
So it seems that this is a really weird science policy which is hugely impacting politics, and there's a feedback, and there's a lot of uncertainty. And there's costs if you do the action. Suppose there's just two states of the world, either we're going towards this disaster scenario or we're not. There's costs if you act and you shouldn't have, or you don't act and you should have. So you should be putting probabilities on these things.
Yeah.
And are you trying to say that we're underestimating one of these probabilities or one of these costs? And the other thing I wanted to say is, to me, if I think of the science of it, everything to me is the water levels. Mm-hmm. Do we flood Bangladesh and Miami and whatever? And so that's basically comes down to, does Greenland melt? Mm-hmm. And it seems like the rise in the temperatures has peaked. Over Greenland has gone up twice as fast as over the Earth. So could there be an acceleration there, and could there be some non-linearities so that we don't really know? That maybe we hit a point where suddenly Greenland just starts to flow into the ocean.
Yeah. So the first minute or so of what you said is correct. It is a risk calculus discussion. And your assessment of that balance of risk really depends on where you sit. So we're in the developed world, got plenty of energy. We could afford to go carbon-free, but we're a small part of the problem, or of the emissions. Whether it's a problem or not, we can talk about. Most of the world is energy starved. Something like half the world uses less electricity than the average US fridge every year. Okay. For them, the calculus, I think, is pretty straightforward. I need the energy now, and I'll worry about what might happen 100 years from now after I've gotten to the level of resilience that you all in the developed world have. Okay. Of course, they're happy if you provide them with carbon-free energy, but they're going to do what they need to do to get the energy, and that means they're going to emit. Right? And you can't blame them. If you were there, you'd probably do the same thing. I like to think it's, what we're telling the developing world is like telling a starving person that they shouldn't eat the piece of steak in front of them because of the cholesterol. Right? First things first. That's in fact what Mr. Gates said. In terms of Greenland, the rate of ice loss in Greenland is highly variable. I've got a graph in one of my other talks. You discover that in the 1930s, it was as high as it was in 2012. And actually for the last decade, it's been going down. So it's influenced by long-term cycles again. And, the amount of, it accounts for a fraction of a millimeter of the current sea level rise currently, and will be less as it comes down, presumably. So I wouldn't worry too much about catastrophic ice loss from Greenland. The so-called marine ice cliff instability that people were worried about 5 years ago, I think has been pretty well disproven. Okay.
Hi, Dr. Koonin. My name is Jonas Shaw. I'm a doctor of climate science, actually.
Good.
And I agree with your summary that climate, is something, but it ain't everything. But I also think that a lot of what you've said has taken evidence and chosen it in a way that I find really misrepresentative of the overall state of the field in the literature that scientists, have contributed with a huge amount of time and energy. And I haven't had the time to prepare that you have, but I would just like the opportunity of this space to address a few of the points that
Please.
you made. It is true that extreme events are difficult to attribute, and this is just because extreme events, by definition, are infrequent. The statistics of detecting that change is challenging. However, things like warming, both globally and regionally, are incredibly robust. Additionally, this idea that changes in the Earth's albedo, this effect that you said about shortwave, somehow disproves the fact that carbon dioxide traps infrared radiation is misleading and actually counterintuitive.
Yeah.
The reason that we're absorbing more shortwave radiation is because this increase in heat has melted reflective surfaces like snow and ice, and it has also changed the way that clouds operate. Our models are not perfect, but we do not need that kind of level of perfection in our models to understand that warming can also modify the way that our planet reflects light. Furthermore, I'd be interested in what your source was when you repeatedly stated that human influence is 1%. What kind of scale, what kind of variables? I found that very, I'll keep going.
Okay.
Also, this idea that the Russian models and the low sensitivity models is also incredibly misrepresentative. I could pull out multiple sources that would show you that these low sensitivity models are not the best models. There is a lot of spread in models, and we call that model diversity. It helps us understand where we are uncertain, and when the models disagree, we should be rightfully critical of them. But we can also take models and use them where we have shown them to perform well. If a model is a good representation of both variability and change in one region, we should use it in that region to detect change. And this is how we can take this variability and we can collapse it into useful statistics. I'll also say that the DOE report, it's great if one scientist comes out and says that they disagree with it, but the comparison with Nazi Germany I find honestly a bit insulting. The fact that multiple people are coming out in this climate where there is, things are complicated, but you can also be punished for being critical of this administration. I'll also say that the idea that 1.5 to 1.8 degrees of warming that we're doing pretty well right now is also misleading. I'm 29 years old, and I know that the climate is changing because I grew up in a time when the way that snow operated was very different in the Midwest. And there is variability. I wasn't here in the 1930s, but we can quantify that really low frequency variability. We can partition it to things like ocean circulation that we can measure, and we can separate the human influence on climate. So the idea that we don't know why the fluctuations are happening is also, I find, incredibly misleading. The idea that temperature and prosperity are linked is a fallacy of causation. That's the reason that, that human prosperity has increased in the last decade is not because temperature has increased. I think that, logically, we can all understand that that is because huge technological advances. And those advances will absolutely allow us to adapt to climate change, but those advances will also allow us to limit its impacts. So yes, GDP is not synonymous with human well-being. That's kind of the notes that I made, but I really appreciate, this forum is a really good place to discuss, and I'm happy to hear your response, but overall, I do find that you've chosen your evidence to benefit an argument that you've been trying to make.
Let me just respond to one specific point and then make a general response. Where does the 1% come from, right? The radiative forcing is 2.5 watts per square meter. The background flows of solar and infrared energy when the planet is in balance, as it approximately is 244 watts per square meter. 2.4 watts is 1% of 244, okay? When you put the CO2 into the atmosphere, you're changing the infrared opacity from 0.83 to 0.837 or something. That's 1%. Okay? And in fact, the formalism that is used to describe the response of the system to human influences is standard linear response theory, which is familiar from many body physics, for example, feedbacks and all of that, which you use when the perturbation is small. So that's why it's a 1% effect. The, more generally, I appreciate the points. I've heard them before. One of the problems is we do not have a forum in which people like you and people who wrote the report, like me, can sort it out, all right? And so what I would offer is that if you want to get some of your colleagues together and write down with quantitative detail the criticisms, I'll bring a group back and we can have a public debate after everything gets written down, point by point, and let people at least understand where we agree and where we disagree. Okay?
Thank you. Can I make one last statement? Okay. Thank you.
Hi, Steve. We were colleagues together at NYU a few years ago. Good to see you again. So on a totally different point, I think that both sides of this debate, or if to the extent that there are sides, agree that with your second bullet point there, that better observations and understanding of the climate are really important. And so I'm the director of the Data Science Institute here now, and one of the things that I find dismaying and confusing is this, maybe it's just a reaction to, what's perceived as like a, climate, hysteria or something like that, but like trying to shut down our observational capabilities. And I'm just wondering if you have any, thoughts about that, if the group that you're convening, since it's probably being paid attention to a lot by people who are wanting to kind of counteract whatever the other narrative are listening, somehow having a robust voice that, like, let's not shut down our observational capabilities or the investments in simulation or even these other things about emission light technologies, that somehow unfortunately seems to be the case. I'm just curious about your thoughts and how the community can...
So that report that I showed you was not supposed to produce recommendations, but we couldn't resist, and in particular, I couldn't resist a few. And the first recommendation there is to keep watching the system with continuity, precision, diversity of metrics. Absolutely important from a scientific point of view. The problem is, it's a political problem more than anything else, most of the US Global Change Research Program budget goes into a couple of big space-based assets, as you may know, satellites that are observing whatever. And it's kind of hard to cut those and still keep the observations going. But, whatever we do, we got to keep watching.
Yeah, and also, I mean, things like ground-based, like Mauna Loa and Mauna Kea, it seems like probably pretty cheap in comparison. So anyways, I would encourage you and your group to double down on that message.
Yeah, good. Well, that's science, right? Science is observation.
Steve, one of the immorality argument, I was reminded of a book by Angus Deaton. Case and Deaton wrote this book called Debts of Despair. And 99% of economists would agree that free trade is a good thing. But how do you get the winners to compensate the losers, right? So how do you get America, that's kind of benefited from polluting, I guess, to compensate those or restrict other countries from not? Is that the kind of argument you have in mind? Do you see similarities?
Yeah, in the Conference of Parties discussion, which is going on now in Brazil, or will start in a couple of days, the central point of contention has devolved to how do the developing countries get compensated by the developed countries for not emitting. Right? I used to like to say, who will pay China not to emit? And the answer is that the sums involved are just so large that you cannot imagine the developed world paying the bill. Plus, we don't have all that much money to spare anyway. So we're going to keep emitting, and we will adapt. That's what we do. We should be helping those countries adapt, of course. And the best way to do that is to help them improve their standard of living, which means get them the energy they need.
Let me end with this. universities, research universities especially, depend a lot on federal grant dollars. I would argue, I've actually written on this, not my original work, but NIH funding, for instance, has an incredibly high rate of return. I would guess it's far greater than any other form of governmental investment. I suspect it's the same for DOE and also for basic science. So how do we get back in a position where we build back public trust in research, in higher ed, and get back to a happier place?
Well, I think, you know, the official institutions, the government, the professional societies, the UN in the case of the climate, start by giving a good factual representation of what's going on. And I think a lot of the distrust has been because there are enough people who read the back of the reports and understand that the politicians and the summaries for the politicians are just inaccurate. And so I think the report we wrote has catalyzed a healthy debate and maybe changed a few people's minds, including Mr. Gates, about what the science is really saying. We should have a good debate about whether it is a misrepresentation or not. We are more than willing to engage. The problem has been getting significant engagement from the people who are promoting the consensus.
Thank you. I think we're out of time. Okay. On behalf of UW-Madison, I want to thank you for making the trip down here. Give Stephen a big round of applause for making the trip down. And I think